All right, in this next section, we're going to cover changes in the state of matter. So let's just imagine our three different states of matter. We're going to do solid over here. I'll do liquid in the middle. And I'll do gas over here to the right. Well, let's imagine that we're absorbing heat. Okay? And if you remember, if we absorb heat during any sort of process, this is called an endothermic reaction. Meaning it's not kicking out heat at the end, it's absorbing heat in the beginning. Okay, so let's imagine this. If we go from a solid to a liquid, this is just called melting, right? All right, sometimes you may see this called fusion. However, that's not commonly used. Melting's generally used when we're talking about a solid converting to a liquid. And then same idea, if we think about a liquid going to a gas, this would be called evaporation or vaporization. So let's just write that down. And a lot of people would kind of think, well, this is it, right? You can go from a solid to a liquid and a liquid to a gas. But there's actually a third one that's pretty important to remember. You can actually skip the liquid phase and go straight from a solid to a gas. So a good example of going from a solid directly to a gas is dry ice. So if you've ever played with dry ice or seen dry ice, you'll notice that it never melts. It's just carbon dioxide in the solid phase, and when it heats up, it goes directly to a gas without going through the liquid phase. This is called sublimation. All right, so these are the three phase change processes for absorbing heat up here. So let's go ahead and think about the opposite. So let's imagine the same thing, but this time we're going to be releasing heat. And this is going to be our exothermic pathways. Okay, so we're still going to have the same states. So I'm going to just put solid over here, and I'll put liquid in the middle, and I'll put gas over here. But let's imagine kind of the reverse processes, right? So let's imagine this time we're going from a liquid to a solid. Well, if you think about that, that's just called freezing or crystallization. So we can take liquid water and freeze it, or in some cases, we'll call it crystallization. And same thing, we can go from gas to a liquid. This is called condensation. You may see it shown as liquefaction. I normally just teach condensation because that's the term we're most used to. In addition, you can imagine the reverse process through which you go from a gas to a solid. So the reverse of our sublimation that we saw up above. And this is just called deposition. It's actually pretty common in the semiconductor industry. You may need to put on like a really, really thin layer of some sort of substance. And you do that by heating up a metal, get it to the gas phase, and get it to deposit on some sort of solid surface. This is often referred to as condensation. So condensation can be a process through which a gas goes to a liquid or a gas goes to a solid. Whoops, I had an extra letter there. So here's the two main pathways. Like I said, the top one's absorbing heat, the bottom one's releasing heat, but it allows us to convert between these phases of matter. What I want to do next, though, is focus on one specific process. So in this first step, let's focus on evaporation or vaporization, and let's compare that to these condensation pathways. So I guess what I'm trying to say is let's focus on getting to a gas from a liquid, and then from a gas back to a liquid or a gas back to a solid. So let's compare and contrast these. Oh, evaporation, not evaporization. evaporation, vaporization versus condensation. All right, so let's take a look at each of these kind of separately. So let's start off with our liquid to a gas, right? So we said that we can go from a liquid to a gas, and we said that this process was known as vaporization. All right, and we said that vaporization is going to be endothermic. It's a heat absorbing process. But what I want to do is show you a figure here. And in this figure, we've got some liquid in a jar. And I know this is a little confusing when you first look at it, but imagine initially over here, you're just putting liquid into a brand new jar and then quickly cover the lid. What will happen is over time, some of these molecules will get ejected off and kind of evaporate up into the open air portion in the top of the chamber. After a while, though, more and more will start ejecting off kind of up here. But the whole idea is you have to reach some sort of equilibrium. And an equilibrium basically means that the molecules that are being ejected off are occurring at the same rate as them going right back into solution. Basically, this just means that things have stabilized and you have a constant liquid level, which is what's shown with that bubble there. So at this point, this is a really crucial point. You've got a lot of gas. And this gas up here has pressure. So this is called the vapor pressure. Of the liquid. So all liquids have this, right? If you think about having a closed bottle of water, not all of that water in that water bottle is going to be in the liquid phase. In fact, some of it is going to be up in that headspace of the water bottle. You'll have some water molecules kind of flying around. And after, in a few hours or a few days, it's going to reach equilibrium and it's going to have some vapor pressure. That's going to be the water molecules exerting force outward on the sides of the container. So we've got vapor pressure as a new term we need to consider. So let's try to define that. And vapor pressure is the pressure exerted, by vapor that is in equilibrium with a liquid. You can actually have vapor pressure for solids as well. So some solids will actually have a significant amount of vapor pressure. A good example of that is solid iodine actually releases a fair amount of iodine as gas. But in that case, it's more of a sublimation process. But for right now, we're going to focus on vapor pressure of liquids. All right, some important notes to think about is that lighter molecules have higher vapor pressure. So then the question is why? I'm just going to abbreviate vapor pressure VP. So why would lighter molecules have a higher vapor pressure? Well, you can imagine in this process of them being kind of ejected out of the liquid phase into the gas phase, if you're lighter, it's going to take less energy for that process to occur. Therefore, more of the light molecules are going to be in the gas phase, which is kind of cool to think about. All right, here's another thing I wanted to show you that's kind of weird with vapor pressure. And let me see if I can grab the right one. Here's the vapor pressure of water at various temperatures. So this is the second one, is lighter molecules have higher vapor pressure, and then vapor pressure increases with temp. So these are the two main things to be aware of whenever we're talking about vapor pressure. In fact, if you see the temperature of water going up, you can see the vapor pressure going up with it. So it's directly correlated. All right, so now let's think about the reverse process. We've talked about things going into the gas phase, that's vaporization, but let's imagine the reverse process, condensation. And condensation is when you have a gas that goes to a liquid or a solid. We're going to use both of these interchangeably, and it's important to remember that this was exothermic, meaning it releases heat in the process. I'm not going to get a whole lot into this, but essentially it's the reverse. So if you have a lower temperature, like in the morning, you're going to get more condensation on your car, right? Because those water molecules that were vaporized during a hot, sunny afternoon are going to slowly condense onto cold surfaces. So the opposite trends are true here that we saw in table 6.5. So condensation typically is favored at cold temperatures. All right, I did want to make an important note, though, that confuses a lot of students. A lot of times students will say, well, vaporization, you're talking about boiling, right? So evaporation is different from boiling. Boiling has a very, very defined property, or very defined set of metrics it has to meet. So the boiling point of a substance occurs when the vapor pressure equals the atmospheric pressure. All right, so boiling is different than evaporation. If you think about evaporation, your dog bowl, if it's left out for weeks and weeks and weeks, that water will evaporate, but it's not boiling. Boiling is a unique phenomenon where the vapor pressure equals the atmospheric pressure. But like I said, we can increase vapor pressure with temperature, which makes a lot of common sense, right? If you heat something up hot enough, the vapor pressure is going to get higher, 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 higher. And you'll notice down here, if you heat water to 100 degrees Celsius, its vapor pressure is now the same as the atmosphere. So same as atmosphere, at least at sea level. Therefore, this is the boiling point. All right, so it is kind of nitpicky. I just don't like students when they look at this flowchart that we did at the beginning saying that this process right here of a liquid going to a gas is boiling. No, it's evaporation. Boiling is a very defined term, and we have to be careful with how we use it. All right, I did want to show you a couple of other things regarding boiling point. So the first one, actually, let me get rid of this square, is that standard boiling point is at 1 atmosphere. All right, so if you, let's say, order, pull up a recipe from the internet and it says to boil something, it's assuming that you're at sea level. The same is true in science, right? We're going to just assume 1 atmosphere because we don't want to write a million instructions for people all over the planet. But I'll show you the problem with that. All right, so here's one problem. Is boiling points change depending on how far above or below sea level you are. So if you think about sea level, the boiling point of water is 100 degrees, but this one down here always blew my mind. That Mount Everest, if you're at the top of Mount Everest, water will boil at 76.5 degrees because the atmospheric pressure is lower. You've got a lot less air above you exerting pressure down, therefore you can boil water at a lower temperature. In fact, this becomes kind of a problem I've heard on Everest because you get more energy from food when it's cooked, but it's harder to cook food at higher elevations. All right, there's one other one. Shoot, I keep on doing the square. And this other one is kind of a one that's pretty popular with home cooks now. I'm sure a lot of you own like Instapots or pressure cookers. But if you have a pressure cooker, you can increase the pressure, which will also increase the boiling point of water. So sometimes people will wonder, well, how does a pressure cooker actually cook faster? Well, it gets around it by actually increasing the boiling point of water, which cuts down the cooking time. So a lot of these Instapots go up to about 15. I think some even go to 20 or 25 psi, which will get you a much higher boiling point. So these are kind of neat things to think about whenever you're dealing with water boiling. All right, so let's go ahead and finally put a square around this just because I want to box it off into its own unique section. All right, so now let's go to our last one. Our last one is going to talk about sublimation and melting. All right, so that's basically when you have a solid going to a gas, that's sublimation. Or melting is when you have a solid going to a liquid. And like I said, it just depends on the solid you're working with. If you're working with dry ice, which is solid CO2, it'll go directly to a gas at room temperature. However, if you've got solid CO2 and you pressurize it at a really high pressure, it'll actually go through the liquid stage. So all of this is dependent on pressure. In fact, if you've got solid dry ice and you have it at high pressure and it goes through the liquid phase, it's actually a really good solvent for pulling caffeine out of coffee beans. And so in fact, you can actually decaffeinate coffee that way. That's what they do for a lot of new decaf coffees. Kind of neat. All right. And another thing to remember is that this process right here, a solid going to a liquid, occurs at a melting point. And this melting point, we're going to talk about it more later, but it's important to think about this occurring at one set value. It doesn't occur over a long range of temperatures. It just occurs at one specific temperature. All right, one other note to think about that's kind of weird to think about, but it's important, especially in organic chemistry, is that some molecules or substances will decompose before a phase change can occur. So not all substances will melt, right? And if you really just think about this, this is common sense. So imagine that you've got a pizza in your oven. Your pizza is going to be a solid. If you heat it up for a long period of time, will it become a liquid or a gas? No, at least I hope not. Instead, it'll actually go through a process of decomposing. That's where it's reacting with the oxygen in the air, oxidizing. You're typically left with, a burnt pizza in your oven. So not all molecules do this, only some of them do. So that's an important caveat. All right, I hope this helps. I know we went through a number of sections. If you do get confused with any of this, the book goes into it in a lot more detail, but I tried to kind of smush this down into what I thought the key parts were. All right, good luck studying.